Welcome back to G Fun Facts Online. Today, we are abandoning the comfort of the studio and taking a journey to the absolute extremes of our planet. I want you to imagine standing on a vast, blindingly white plateau. The wind is howling, and the temperature plunges to -80 degrees Celsius. Beneath your boots lies a library of water, frozen in time, stretching down over 3 kilometers into the bedrock. This is not just ice. It is a vertical archive of our planet's history, a high-fidelity recorder that has been capturing the breath of the Earth for millions of years. Every snowfall that has settled here since the dawn of humanity has trapped tiny bubbles of ancient air, preserving the atmosphere of the past in microscopic time capsules. This is the world of paleoclimatology and ice core science. It is a discipline that combines the grit of extreme exploration with the precision of atomic physics. It is the science that has definitively shown us how our climate works, how it changes, and where we are heading. In this episode, we are going to drill deep into the ice sheets of Antarctica and Greenland. We will journey through the history of this fascinating field, explore the engineering marvels used to extract these frozen cylinders, and decode the chemical secrets that have rewritten the story of Earth's climate. To understand why this matters, we first have to define what we are actually doing here. Paleoclimatology is the study of climates prior to the invention of meteorological instruments. We cannot hop in a time machine to measure the temperature of the Eemian interglacial period 125,000 years ago. So we rely on proxies, which are imprints left on the natural world by past climate conditions. You might have heard of tree rings, coral reefs, or ocean sediments. They all tell part of the story. But ice cores are considered the gold standard of paleoclimate proxies. They are unique because they are the only archive that preserves direct samples of the ancient atmosphere. When you pop a bubble in an ice core from 20,000 years ago, you are breathing the exact same air that woolly mammoths breathed. So, how does ice become a time capsule? It all begins with a snowflake. In the polar regions of Antarctica and Greenland, snowflakes accumulate in layers that do not melt during the summer. As years pass, new layers bury the old ones. The weight of the accumulating snow compresses the layers below. It transforms first into granular snow, known as firn, and eventually into solid glacial ice. As this snow compacts, the air spaces between the crystals get sealed off. At a depth of about 60 to 100 meters, known as the lock-in zone, these pockets of air are pinched shut, becoming permanently trapped bubbles. The ice acts as a 3-part recording device. First, the ice matrix, the water molecules themselves, record the temperature at the time of the snowfall. Second, the gas bubbles trap greenhouse gases like carbon dioxide, methane, and nitrous oxide, revealing the composition of the atmosphere. And third, the impurities trapped in the layers, things like dust, volcanic ash, sea salts, and even pollution from ancient Roman lead smelters, tell us about wind patterns, volcanic eruptions, and human activity. Now, the quest to retrieve this ice is a story of scientific heroism. It really began in earnest during the International Geophysical Year of 1957 to 1958, which saw the establishment of permanent bases in Antarctica. One of the most fascinating chapters in this history involves the U.S. Army in the early 1960s. They built a nuclear-powered base inside the Greenland ice sheet called Camp Century. The military goal was essentially to test if they could launch missiles from beneath the ice, a project known as Project Iceworm. But scientists used the opportunity to drill the first deep ice core. The result was a revelation. The layers of ice could be read like the pages of a book, revealing rapid climate swings in the deep past. Later, during the Cold War, Soviet scientists at Vostok Station, the coldest place on Earth, drilled a hole over 2 kilometers deep. In the 1990s, a collaboration between Russian, French, and American scientists analyzed this core. The Vostok core became legendary. It provided a climate record going back 420,000 years, covering 4 complete glacial interglacial cycles. The resulting graph was the smoking gun of climate science. It showed a near-perfect lockstep between carbon dioxide and global temperature. When Colorado 2 went up, the temperature went up. When Colorado 2 went down, the planet froze. This ushered in a golden age of drilling in the 1990s and 2000s. In Greenland, 2 rival projects, GISP2 and GRIP, drilled just 30 kilometers apart. They discovered something terrifying. The climate of the northern hemisphere is capable of abrupt changes. They found evidence that temperatures can skyrocket by 10 degrees Celsius in just a few decades. Meanwhile, in Antarctica, the European Project for Ice Coring in Antarctica, or EPICA, drilled at Dome Sea, retrieving ice dating back 800,000 years. This remains the longest continuous climate record we have published to date. But how do we actually get this ice? Drilling an ice core is like performing laparoscopic surgery on a continent. It is often done in conditions where hydraulic fluids freeze and metal becomes as brittle as glass. In the early days, scientists used thermal drills, essentially a heated ring, to melt their way down. But this was slow and often contaminated the chemical signals. Modern projects use electromechanical drills. Imagine a hollow, rotating drill barrel with razor-sharp cutters at the bottom. As the barrel spins, it cuts a cylinder of ice. Now, here is a critical engineering detail. Ice sheets flow like slow molasses. If you just drill a deep hole, the immense pressure of the surrounding ice will squeeze the hole shut. To prevent this, the borehole is filled with a fluid that has the same density as ice. This keeps the hole open, but it requires strict environmental controls to prevent pollution. A day in the life of a driller is intense. They work in 24-hour shifts during the short polar summer. The drill is lowered on a winch cable thousands of meters down. It takes hours just to travel to the bottom, cut a 3-meter section of core, and winch it back up. When the core surfaces, it is treated like a newborn baby. Scientists work in clean rooms, which are often trenches dug into the snow to stay naturally cold. They wear sterile bunny suits to avoid contaminating the ice with skin cells or fibers. The core is logged, measured, and cut into sections. Some are analyzed in the field, while others are packed in insulated boxes and flown on military cargo planes to labs in Denver, Copenhagen, or Bern. Once the ice reaches the lab, the real detective work begins. You might be wondering, how do we know the temperature from 500,000 years ago? We use a technique involving water isotopes, essentially using them as a paleothermometer. Water is made of hydrogen and oxygen. Most oxygen atoms have 8 protons and 8 neutrons, known as oxygen-16, but some have 10 neutrons, known as oxygen-18. This heavy oxygen is harder to evaporate and falls out of clouds faster. In cold climates, the heavy oxygen-18 rains out before it reaches the poles. So the snow that falls in Antarctica is depleted of heavy oxygen. In warm climates, more energy drives the heavy oxygen all the way to the poles. By measuring the ratio of heavy to light oxygen in the ice, scientists can reconstruct the precise temperature at the time the snow fell. Then there is the gas analysis. To analyze the ancient atmosphere, scientists place a chunk of ice in a vacuum chamber and crush or melt it. The ancient air bubbles pop, releasing gases trapped for millennia. We can measure the exact parts per million of Colorado 2 and methane. This has proven that pre-industrial Colorado 2 levels never rose above 300 parts per million in the last 800,000 years. Today, we are over 420 parts per million. There is a tricky part to this science, though. The air is always younger than the ice that surrounds it. Remember the lock-in zone? The bubbles do not close until the snow is buried deep in the firn. So, scientists must use complex models to correct for this gas age-ice age difference. Finally, We analyze the impurities using a technique called continuous flow analysis. Scientists melt a stick of ice from one end to the other, feeding the meltwater directly into mass spectrometers. Spikes in sulfates, or visible ash layers, indicate massive volcanic eruptions. These serve as time markers to synchronize ice cores from different parts of the world. Sea salt tells us about ancient sea ice extent, and cosmogenic isotopes like beryllium-10 tell us about changes in the sun's intensity and Earth's magnetic field. The data ripped from these frozen cylinders has fundamentally altered our understanding of Earth. First, ice cores confirmed the Milankovitch cycles. These are the changes in Earth's orbit, tilt, and wobble that pace the ice ages. However, the ice cores reveal that these solar nudges are too weak to cause ice ages on their own. They need an amplifier. That amplifier is carbon dioxide. Second, we have the hockey stick context. For 800,000 years, carbon dioxide oscillated naturally between 180 parts per million during glacial periods and 280 during interglacials. The vertical spike we see today is visually shocking when plotted against those gentle waves. It proves unequivocally that modern warming is not natural. Third, and perhaps most alarming, is the discovery of abrupt climate change, known as Dansgaard-Oeschger events. During the last ice age, the climate was wildly unstable. There were 25 distinct events where temperatures in the North Atlantic skyrocketed by 8 to 15 degrees Celsius in just a few decades. These flickering switch moments are believed to be caused by the shutdown of ocean currents. This suggests the climate system has tipping points that, once crossed, cause rapid, irreversible change. Right now, we are in the midst of the most ambitious ice core project in history, known as Beyond EPICA. We have a puzzle to solve called the Mid-Pleistocene Transition. About 1 million years ago, Earth's climate rhythm changed. Before that, ice ages happened every 41,000 years. After that, they slowed down to every 100,000 years and became much more intense. Why did the heartbeat of the planet slow down? Did Colorado 2 levels drop? To answer this, we need ice older than 800,000 years. Finding this holy grail of ice is difficult because geothermal heat from the Earth melts the bottom layers of thick ice. Scientists had to find a Goldilocks zone, a place where the ice is thick enough to be old, but the heat flow is low enough that the bottom hasn't melted. They found it at Little Dome C in Antarctica. As of 2025, the European team has drilled down nearly 2.8 kilometers, reaching ice believed to be 1.2 to 1.5 million years old. At this depth, the pressure is so immense that air bubbles actually disappear. The air molecules get forced into the crystal lattice of the ice itself, forming clathrates. The ice becomes perfectly transparent, like glass. Paleoclimatology is not just about the past, it is a forecast. It tells us about sensitivity. By looking at how much temperature changed when Colorado 2 rose in the past, we can calculate how much warming we should expect from our current emissions. It warns us about sea level rise. Ice cores from the Eemian period show that with temperatures just 1 to 2 degrees warmer than pre-industrial times, exactly where we are now, sea levels were 6 to 9 meters higher. This tells us that our current ice sheets are incredibly fragile. And it warns us of tipping points. The evidence of abrupt changes in the ice shows that we may be poking a beast that reacts with sudden violence. The ice sheets are the memory of the world. They have watched continents drift, civilizations rise, and volcanoes darken the sky. Through the tireless work of paleoclimatologists, these frozen archives have given us a warning. We are pushing the Earth's atmosphere into a state unseen for millions of years. Drilling these cores is a race against time in two ways. We need the data to understand our future, but the archives themselves, the mountain glaciers and ice sheet edges, are melting away. Every meter of ice lost to warming is a page of history torn from the book of Earth, gone forever. That is all for today's deep dive. Thanks for listening to G Fun Facts Online.